Hello class, welcome to lesson 5.5. So we're going to talk about inequalities in two triangles. So the question that we want to address today is when triangles have two pairs of congruent sides, how are the third pair of sides and pair angles opposite the third pair of sides related? So what's the relationship between those third pair of sides? So we want to compare the pair of sides of two triangles when the remaining ones are congruent. So we're going to investigate what we refer to as the Hinge theorem. So if you look at these two triangles, notice that they have the same measurements here and here. So those pair of sides are the same, and in this case, these two pair of sides are the same. And so what we want to address is, well, how many different, you can see that these are two different triangles based off of the third side, the different measurements on the third side. And so what we want to see is, well, what happens as we adjust this included angle between the two sides that are congruent. And so that's what we want to look at to see if there's any relationships between the angles and the included angle in that third side. So you can see that as we're adjusting the angle, that third side is adjusting accordingly. So as that angle is increasing, that third side is increasing. And if I adjust the other side, notice that that other side staying the same, adjusting the angle has the same relationship. So even if I change that second side so it's the same on both, it still has the same relationship. So as I increase that angle, that third side is going to increase. If I'm going to increase it all the way, it'll lengthen. All right, so this phenomenon is known as the Hinge theorem, and so we want to investigate it. So a Hinge theorem is kind of akin to a door hinge. So it's not unlike that. So when so in this case, you have door 1 and door 2. We're assuming the doors are the same dimension, and the frame of the door is also in the same dimension for this purposes of this example. So clearly door 2 is open more widely than door 1. And that's the idea here. And so what we want to do is we want to construct a triangle, and we can do it on the top or on the bottom. So we'll do it on the floor here. And again, we're assuming that the door is the same dimension and the opening space is the same dimension. So therefore, we have the same scenario that we had in the clip that I showed you. Now, we want to compare the opening, the third side here. So the door that is open more widely is the door that has the greater distance on that third side. And so we want to look at that angle there. So again, as we mentioned, if one door is open 75 degrees and the other door is open 90 degrees, for instance, then how are the third sides compared? Well, let's call the third side A and B. And as we mentioned earlier, the greater that angle in between, the included angle, the greater the distance on that third side. So and therefore B is greater than A. All right, so that's the investigation of the Hinge theorem. Let's go ahead and define the Hinge theorem. So if two sides of a triangle are congruent to two sides of another, and the included angles are not congruent, then the longer third side is opposite the larger included angle. So in this case, the included angle is the angle between the two congruent sides right here. So it's saying that the left angle is, if the left angle is greater than the right angle on the right triangle, then the opposite side is larger for the larger included angle, and therefore XY is greater than BC. So we're going to go ahead and prove the Hinge theorem, and we're going to do this. We're just going to kind of explain through it. We're not going to do a 2-column proof or anything like that. We're just going to kind of do like a paragraph proof. Okay, so first what we want to do is we want to construct a triangle to make this work, because right now we have two triangles here, and we want to essentially put it in one triangle in one diagram, like one compact diagram, so that we can compare these sides more directly. Okay, so I'm just zooming in on the left triangle on the left, and I'm going to essentially superimpose the triangle on the right onto this triangle so we can compare. So I'm going to basically reconstruct that triangle so that we can compare them, knowing that that bottom side is the same, so it basically is on top of the bottom part of the left triangle. Okay, so now I have a diagram that I can use to compare the triangles directly. So what we want to do is I'm going to draw an angle bisector from point W onwards, and now point W is the same thing as point A, you can see, and point X is the same thing as point B, so just keep that in mind. So I'm going to do an angle bisector from W or A to the other side of the triangle X on XY. And so I'm going to label that point H where it crosses XY. And there's a reason that I'm going to be doing this. I'm going to show you. So I'm going to make a triangle out of this here and here. So that's two triangles that I just made on here. And I'm going to use the relationships of these triangles to help me with the proof. All right, so we know that AC is equal to WY based off because of the triangles that's given. And I constructed it so. And because I said that I was trying to draw an angle bisector, that means that angle YWH is congruent to angle CAH, which are the blue angles that I just mentioned here. So by construction, those are the same because I constructed an angle bisector. So now we know that AH is congruent to AH by the reflexive property, which is this angle bisector here. That is the same, congruent to itself. And the reason why we do this is because we want to show that the triangles are congruent. We want to show that YWH and CAH are congruent by SAS. So that's the two halves here and here, those two triangles. We're showing that those two triangles are congruent. So why is that important? Well, because we can use CP/CTC to show that HY is equal to HC. So now we basically know that this distance is the same as that distance. And that's going to help us with the relationship we're going to do next. So using triangle XHC, which is this triangle here, XHC, using that triangle, we can do the triangle inequality theorem. Remember, the triangle inequality theorem states that you can add the two sides, right? And it has to be larger than the third side if you want it to be a triangle, which this is a triangle, and therefore it has to satisfy the triangle inequality theorem. So we have XH plus HC has to be greater than this side, and therefore that's what's illustrated in this triangle inequality theorem. But we know that HC is equal to HY because of this step here, and so we're going to do a substitution. And so now HC gets replaced with HY. All right, and so now by segment addition postulate, we know that XH plus HY is equal to XY. Right, that whole thing. So this piece plus number 2 piece is equal to the third piece, this long piece here. So 1 plus 2 is equal to 3. And therefore we can replace this sum right here with XY. So doing another substitution, we can clearly see that XY is greater than BC if we replace this sum with XY. And so now we went ahead and we were finished with the proof. We proved that XY has to be bigger than BC. End of proof. All right, so let's go ahead and use the Hinge theorem. So we want to order AB, BC, and CD from least to greatest. So if we want to order this from least to greatest, first off, we need to figure out all the angles. Notice we have 3 triangles in this Hinge theorem. So sometimes that'll happen. But most of the time you'll have, you're going to have at least 2 triangles. But in this case we have 3. So we're going to try to figure out this angle here. So notice that all these triangles satisfy the Hinge theorem because we always have 2 sides that are the same. So that one, that one, that one, right? So each triangle has 2 pairs of congruent sides. All right, so we can compare them directly. And so if this So notice that this right here adds up to 180 because this is a straight angle. So those three angles have to add up to 180. So that means that let's figure out what that is, x. So we got a 58 plus 56 plus x is equal to 180. And then we can figure out the unknown angle here. So 58 plus 56 is 114. Can subtract 114 on both sides. And so we get 56 degrees. Yeah, that's 56 degrees. No, it should be 66 degrees. And then, so now we got this is 66 degrees, so we're going to go ahead and replace that. Okay, so now we got our angles. So now we can compare which one is largest. So we want to look at the opposite side of each angle. And then that, so AB refers to 58 degrees, right? And then the opposite side of this angle and the opposite side of this angle. And so based off of the numbers, BC is the largest because 66 is the largest, AB is the second largest. So, and it says the least to greatest. So let's do the smallest. So the smallest is the 56 degree angle. So opposite of that is CD. So CD is smaller than the next smallest is AB. And then the greatest is BC. And that's it for our example. Okay, so now we're going to discuss the converse of the Hinge theorem. So this is the reverse of what we discussed earlier. So this time, if two sides of one triangle are congruent to two sides of another, that hasn't changed. We have to have that for the Hinge theorem or the converse. But this time, the third sides are not congruent, then the larger included angle is opposite the longer third side. So this time, if the sides are longer, so if we know that this is longer than this, say 10 versus 8, then that means that the opposite angle, the included angle, has to be larger for 1 as opposed to the second triangle here, okay? So you're doing the backwards. So instead of going from the angle to the side, you're going from the side to the angle, to comparing the angles here directly. All right, so let's prove the converse of the Hinge theorem. So in order to prove this, we're going to prove it indirectly. So we're going to do what we call an indirect proof, and proof by contradiction. So we want to basically assume, so basically we want to prove that this is greater than this, right? But we're going to assume by contradiction that, let's assume that it's not greater than, okay? So instead of trying to prove that it's greater than, we're going to assume that it's not greater than, which means that we're going to assume it's equal to or less than. And then if we see any contradiction, then that means that our assumption is incorrect, which means that it has to be greater than. Okay, so that's how the proof by contradiction works. So we're going to prove this indirectly. So let's assume that instead of it being greater than, we're going to assume the opposite. We're going to assume that it's equal to or less than. Okay, so if we show that there's a contradiction for both of those, then that means that the greater than assumption should have been correct, okay? All right, so first case, assuming that it's equal to, so let's do that case first. That's so if it's equal to, then that means that if these are equal, which I will indicate these with the arc to show that they're equal, so let's say that they're equal, well then that means that they're congruent, right? And if they're congruent, then we can say that those triangles have to be congruent by SAS, right? Because we got a side, an angle, and a side, an angle, and a side, if that were the case. All right, so those triangles are congruent then. And so if they're congruent, that means that EF is congruent to UV by the CP/CTC, the corresponding parts of congruent triangles are congruent theorem. And so therefore EF has to equal to UV, right, by definition. However, that contradicts what we just said. That contradicts what we know about the triangles. We know, because it's given, that EF is greater than UV. It can't be equal, right? So there's a contradiction here, and therefore the assumption that FDE is equal to M or VTU is incorrect. And therefore, so far, we're halfway there to prove that it should be greater than and not equal. So now we're going to prove the second case that it is less than. So we're looking at this now. So let's go ahead and look at that case. So let's assume that it's less than for the second case. And therefore, if that's the case, well, EF has to be less than UV by the Hinge theorem. Remember that we're trying to prove the converse of the Hinge theorem, but we already proved the Hinge theorem, the regular Hinge theorem. So we can use that here. If this is at less than that angle, right? So if this is smaller than this, and this is larger, well, then that means that by the Hinge theorem, that opposite side, FE, has to be smaller than VU, right? UV. But we know that's also a contradiction because we know that that's not the case. We know that EF is greater than UV. That's given in the problem, and therefore we have a contradiction. And therefore, that means that these assumptions are incorrect, which means that the original what we're trying to prove has to be correct. So therefore, that is the end of the proof. It has to be greater than. All right, so now let's look at an example using the converse of the Hinge theorem now that we proved it. So here we want to order the angles PTU, SQT, and angle QSR from least to greatest. So notice that we're doing the opposite of what we did before. Before we were trying to order the sides, and now we're trying to order the angles. So we're interested in this angle here, PTU. We're interested in SQT, and I'm not trying to show that these are congruent by any means. I'm just trying to indicate the angle that we're interested in. And we have QSR. And so in order to use the Hinge theorem, remember, we have to have two pairs of congruent sides. So we need to make sure that that's true first, okay? So if we're trying to, and so basically we're trying to compare the opposite side right here, right? We're trying to compare the PU side, we're trying to compare this side, the TS side, and we're trying to compare the QR side. But before we compare that, we need to make sure that we do have two congruent pairs. So this side is congruent to this side because they're both 7, and they're both have a measure of 7. And which is congruent to this side. So those are all congruent. That makes sense. And then this is congruent to this side. Okay, and so now you can see that each triangle has two pairs of congruent sides, right, between them. So we can use the Hinge theorem here. So the included angle between those two congruent sides. So we're comparing PU. We're comparing TST. And then we're comparing QR. So if we were to compare those, well, we can see that this is the smallest, right? So that's number 1. This is the second smallest, and this is the largest. So in order from least to greatest, it's going to be ST, which is less than QR, which is less than PU. All right, and that is the converse of the Hinge theorem. Okay, so now we're going to include an example here in which we have to figure out a range of values for a given side or angle. Okay, so this one's a little different because we have to include what we know in the previous lesson as well. So we'll discuss that. We'll go through the motions here. So first off, we need to know that, well, can we use the Hinge theorem here? And the answer is yes, we can if we're using these sides. So if we know that these two sides are congruent, which they are, and we know that since these two triangles share this side, by reflexive property, it's congruent to itself, and therefore we can use the Hinge theorem. As long as we're focusing on this angle here and this angle here, the angle between those two sides that were marked. Okay, so then we look at the side opposite of those angles, right, which is in this case AD and CD. So which angle is larger here? Well, we clearly see that 133 is larger than 112, and therefore CD has to be larger than AD, right, by the Hinge theorem. So we know that CD has to be larger than AD by Hinge theorem. And therefore, we can say that, well, AD is 2x plus 17, right? And CD is 39. So I'm going to, since I like the x to be on the left side, I'm going to rearrange this and say that instead AD is smaller than CD, okay? Notice that those two mean the same thing, okay? So that's a symmetric, kind of a symmetric property where, you know, you switch it, but make sure that the sign is switched too. Okay, so AD is smaller than CD, and we know that AD is 2x plus 17, so I'm going to use that here. So 2x plus 17 has to be less than 39, which is CD. Okay, so this is my inequality. Now I want to solve this, right? So if I want to solve this, I'm going to solve it just like any equation. Subtract 17 on both sides. And we have 2x is less than 12. And then divide by 2 on both sides. So x has to be less than 6. Okay, so as I mentioned before, there's more to this theorem than just a Hinge theorem, because we know that x is smaller than 6, but there's another fact that we need to include. Okay, how much smaller than 6 can x be? Can x be 1, 2, 3? Can it be negative? Can it be 0? These are things that we want to address. So the smallest that x can be depends on the triangle that you're looking at. So if we're looking at this particular triangle right here, well, we know that by the triangle inequality theorem, there's a limit to how large this side can be, right? The triangle inequality theorem states that if I add two sides in a given triangle, then it should be if I add two sides, it should be greater than a third side, right? So that's something that we want to keep in mind as well. Also, we know that this side right here cannot be equal to 0. So that's another thing too. So if this side cannot be equal to 0, because then it won't be a triangle, then that's going to be the one that we want to use here. So we're going to say that, well, 2x plus 17 has to be greater than 0. It can't be equal to 0 because we no longer have a triangle. So therefore, this is the one that we're going to use. We're going to go ahead and subtract 17 on both sides here. So this is greater than negative 17, and then divide by 2 on both sides. And so x has to be greater than negative 17 over 2. And so that's the smallest that x can be, just above this number. And the largest x can be is, well, 5.999, just below 6. All right? And so we're going to put these together. And so if we put them together, we get x is less than 6, but it's greater than negative 17 over 2, if we put those two inequalities together. All right, so let's look at another example. This time we're looking at inequalities with the converse of the Hinge theorem. So we're looking at the angles based off of the sides. So we're concerned with these angles here. All right, so what's the relationship between those two angles? Well, we know that we have two pairs of congruent sides, so we can definitely use the Hinge theorem here. So you're going to compare the opposite sides. You're going to compare this 10 here to this 12. All right, so clearly 12 is bigger than 10, and so therefore the 54 degrees is going to be larger than the 4x minus 18, okay? And so therefore the 4x minus 18 has to be less than the 54 because this is smaller, okay? So now we're going to go ahead and solve this. So we're going to add 18 to both sides. And then divide by 4. So we got 72 divided by 4 is going to be 18. So x has to be less than 18. So now we need another inequality. How much smaller can x be? Well, we know that for any triangle, the smallest angle that you can have is 0. Okay, so, and the largest angle that you can have for any triangle is just below 180. Okay, so the smallest is just above 0, like 0.1, and the largest is just below 180. So in this case, well, we already have that x is less than 18, right? So that means that's already below 180. So therefore, what we want to look at is the greater than 0. Okay, so here I'll go ahead and repeat what I just said. So we want to know that, well, this angle has to be greater than 0, and it has to be less than 180. However, we already know that 18 is less than 180, and so we don't have to use this inequality, okay? So we're going to be using this inequality. So let's go ahead and solve that one. So again, we're going to add 18 to both sides like we normally would, and then divide by 4. So now we're going to divide this by 2, top and bottom, and that's going to be 9/2. So if we put these together, we're going to get that x is less than 18, but it is smaller or greater than 9/2. So x is between 9/2 and 18. Okay, so that takes care of A. Now let's look at B. So B here, we have 2 pairs of congruent sides. How do we know that? Well, we have this side, and we have the side that they share here in the middle. So technically, those 2 sides are congruent because it's congruent to itself. All right, so now we can use the Hinge theorem, or rather the converse of the Hinge theorem. We know that this is, so if we're comparing these 2 angles, that angle and this angle, you're going to look at the opposite side, right? Well, in this case, we know that 21 is greater, right, than 16. And therefore, the opposite angle to 21, which is the 3x plus 5, has to be bigger than 32. So we got our relationship here. 3x plus 5 has to be greater than 32. All right, what's my other relationship? Because remember, you usually have another relationship, whether it's greater than 0 or less than 180, right? So for any triangle, has to be just above 0 or just below 180. So if, well, we already have that it's greater than 32. So I'm going to go ahead and rewrite those two inequalities to kind of show you. So remember, for any triangle, any angle has to be greater than 0, but less than 180. So which one makes sense for this application? Well, it doesn't make sense to use the first one because we already know that it's greater than 32, and therefore it's greater than 0, right? So we don't have to use that one. So the only one that gives us new information is the second one. So we're going to use that one. So we have our 2 inequalities. 3x plus 5 is greater than 32, and 3x plus 5 is less than 180. So those are my 2 inequalities, and I'll go ahead and solve those now. Minus 5 here, minus 5 here. So 3x is greater than 27. 3x is less than 175. Divide by 3 for each set of inequalities. So x is greater than 9. X is less than, 3 goes into 175, should be 50, should be, let's see here, it might be a fraction here. 3 goes into 17 5 times. Yep, so that's going to be a fraction. 3 doesn't go into 25, so we're going to leave it as a fraction. All right, so now we know that if we put these together, x has to be smaller than 175/3, but has to be greater than 9. All right, that's going to do it for the video, guys. I hope you found this useful, and as usual, I'll see you in the next one.